Hello, welcome back to Proximity Math. Today I'm going to go over the 2008 AIME II number 8. Okay, let A equal pi over 2008. Find the smallest positive integer n such that this expression is an integer. Okay, we need to find the smallest n so that the summation of, you notice cosine of A sine of A, cosine of 4A sine of 2A, and the pattern's obvious. Cosine of 9A sine of 3A, which is 9A3 squared, and so on until some n squared A in the cosine, and then sine of NA. So there is no general identity, obviously, for some number multiplied by the, there's no like nth cosine of the nth theta, but we can use complex numbers or some product of some identities. That's what you would think of off the bat because they're products. Okay, and let me actually, because I'm a Chad, let me use both ways. Okay, so if we do the complex number way here, and then the is it there? Okay, and then okay, so now first of all, let's see this one. So product to sum, we have the general term being cosine of k squared A times sine of k A. Okay, and using product to sum, actually each term is multiplied by 2, the entire series, so each of these terms would be 2. Okay, this is the perfect form to convert because this would become 1/2 of some sum. So now we can ignore that 1/2. It's multiplied out, and instead you get okay, these two are different, so you would use this two signs identity. And then sine of k minus, okay, it would actually be k minus k squared times A, but if you do a few steps ahead, you're gonna realize that this, you can telescope the series. Like if you list out the first few terms, you're gonna realize they telescope really quickly, because actually we can factor this out really easily. K squared plus k is actually k times k plus 1. Okay, and now this, we can take this, we can invert the sign and swap them. I mean, swap the numbers, and then make this a subtraction instead. So this would become k squared minus k now. Times A. Alright, so, alright, and it's a sum. So we have these terms formally from k equals 1 to n. And what is this equal to? Well, if you have if you increase k by 1, this would become k plus 1 times k, sorry, k plus 1 times k plus 2, while this would become k plus 1 times k, which is the term here. So you would get like for example, it would sine of, for 1 it would be 1 times 2, 8 minus sine of 1 0 8. Oh no, is it 0? Okay, and plus sine of now it's gonna be 2 times 2 plus 1, 6a, minus sine of 2 times 2 minus 1 is 2a. And since you increase k by 1, we just proved it would be the first term of the last sum. And since you're subtracting it like I did, it's going to cancel. And this is also going to cancel, and so on. But this term, when we're done canceling all of them, the first term of the last sum will remain because it cancels this way, not this way, if you know what I mean. Okay. And then dot dot dot, it's going to be the first term of the sum on n. So it's n times n plus 1a. Okay. And then sine of 0 is just 0, so it doesn't matter. And this is our actual final simplified sum. We have the value of a, and we want it to be an integer. Okay. So, what is sine an integer? It's an integer when it can be 1/2, which is when it's 30 degrees, or it can be 1 when it's 90 degrees. Okay. Now, knowing that this is not linear, it can easily skip over 30 and hit 90 or stuff like that. So let's be careful here. Okay. So we want n plus 1 times pi over 2008. So this is a fraction of pi right now, and we want it to be equal to either 30 degrees is pi over 6, or we want pi over 2. We do not want 60 degrees, that's not an integer. Okay, we can ignore the pi's. These become 1s, yes, okay. And then we can multiply by 2008. Whoopsies, okay. So 2008 over 2, or actually, okay, yeah, that would go here. And then I multiply it by 1/6. Is it even divisible? Well, if you sum the digits 2 and 8, it's not divisible by 3, which means it would be a fraction, some fraction. And this is clearly an integer, so we must hit 90 degrees first. Okay, so will this ever be to 1004? Well, we can take the square root and approximate it. You know that 32 squared is 1024, otherwise you're bad. So 31 times 32. If you're using a calculator, you're also bad, so I'm gonna do it in my head. Okay, this is just 32 squared minus 32, which is 1024 minus 32. It's obviously less than 1,000, but it's 992. And if you try the other way, no, it does not work out. So for some integer, not the same key, I'm gonna use x. And now it's gonna be a multiple of this, which is automatically a multiple of 30 degrees. And that was not an integer. Basically, we'll have to multiply the 30 degree fraction by 3 to get this. And then we're gonna hit a 90 degree multiple instead. So basically, it will never be a 30 degree multiple. That's not a 90 degree multiple. We reworked that out earlier. Okay, now 1004x. We can take the factors of this. Divide by 4, it's 251. And let's see. Is 251 divisible by anything really? Not 7. What about not 13? No. Not 11. You know, it could be prime. And actually, it is prime. You can guess that too, if you're lazy. But Now we need obviously we can make n plus 1 be 251, and then n can be 1 less than that, but unfortunately 250 is not divisible by 4. So we can make n equal 251, and then n plus 1 is 252, which is divisible by 4. And it would be so funny if you entered 252 as the answer, but unfortunately n is the smaller one, 251. All right, that's our final answer. But since I'm not lazy, I'm going to do the second method, complex numbers. All right. Now, this is the other approach you would think of immediately because we have unapproachable multiples inside the arguments of the trig functions. So it might have something to do with Weber's formula, the one where you multiply complex numbers. Okay, so we clearly have a sussy root of unity over here. So if we let, that is really bold. It's actually the minimum thickness. Okay. You should know what this means. Sus of A, which is e to the pi A I pi A. Okay. Now then notice that z to the 2008 is -1, or rightfully z to the 4016 is going to be 1. Okay, now then okay, so our general term over here, I wrote it over here to like notice that z plus if we wanted cis of ka, we need z to the k. That's equal to z to the k. And if we use the way to get cosines from that, we're adding the conjugates and the actual numbers. You're adding them, and then we're dividing by 2. That's how you get the cosine. So this would give you the formula for cosine of ka. And then sine, the imaginary part, would be, yes, speedy. Okay. The subtraction of these. Okay, now we have that information. Okay, be careful. Now, our general term over here. So how will we get that? And I'm also going to include the 2. Okay, so if we multiply these together and then also multiply by 2, we're still going to have 1/2 left over. Not 1/4, but 1/2 this time. Okay. And we need k squared a. K squared a. And then sine of ka. Okay. So cosine of k squared a, that would be z of z to the k squared, not 2k. I made the mistake last time. Okay. Minus negative k squared. Okay. Now sine it's just k. It's just the same formula we just did. Okay. Whoops. This one is plus. This one is minus. I know it's going into here. I'm gonna erase this thing. Okay. Equals the sum of this, by the way. This every individual term. Okay. If we multiply this out, z to the k squared plus k. I'm gonna factor it like last time. Okay, like this, and then like this. It's gonna be Yep, okay. And that's gonna be z to the k minus k squared, which is just the conjugate of this. And then if you multiply this, it's z to the negative k times k plus 1, which is the conjugate of this. So the full expansion would actually be, I'm using hacks. Okay. Now, bracket, okay. Negative, negative. Okay. And if we group these, them and their conjugates, we can reverse the formula we used for cosine and sine over here. Okay. So we have k times k plus 1, and both of them are pluses actually. Or are they? Of course I made a mistake. Okay. This is actually a minus sign, so this would be a minus sign. And k squared minus k. This is also a minus sign. Okay. So if we group this and this, okay, cosine. Oh my god. Okay, I got it. Let's go. Okay, let me just multiply to recheck because I'm not getting the same terms as the other method. Yeah, we got this. Okay, this outside. K squared minus k. K squared minus k. Yeah, we get this. Okay. K minus k squared is negative this. Yeah, okay. And then minus, yes. Okay. And actually we're pairing these two, so I made a super funny mistake. And now we're also pairing these two. They're k times k minus 1 and its conjugate. And they're opposite side signs, but we're subtracting this and adding this. So actually, yeah, if you pair them together, but if you can't do the algebra in your head, you're bad. Anyway, if you pair them together and use the formula, you would get this. Oh, yeah. Finally. And you would notice this is the same exact result we got over here. That's because complex numbers and product of sum are actually extremely related, so you can use one to prove the other, especially if you have proved advanced identities. Anyway, from the same exact logic over here, this would telescope to this, and then the same exact logic over here. And by the way, every term is multiplied by 2, so that 1/2 cancels out, and this is a sum because it's of every term. So if you follow the method over here, then you get that this angle must be a multiple of 90 degrees. It can't be of 30 degrees. Otherwise, it'll be, this won't be an integer, but it must be. Okay, so now you would get the divisibility thing and realize the smallest n which satisfies this is 251. So either way, this is our final answer. Thanks for watching, and I hope this helped you.